Every time you snap a photo or stream a movie or honestly just look at your screen, you are interacting with this whole universe of hidden mathematics. It's pretty amazing. Today, we're going to pull back the curtain on the invisible, kind of genius level math that makes our entire digital visual world even possible. All right, let's start with a really concrete example. Just look at this incredible image of a star cluster. It's made up of millions and millions of individual pixels, right? Each one has its own color, its own brightness information. If you were to look at the raw file for this single picture, well, it represents a massive amount of data. We're talking way too much to just quickly send to a friend or, upload to Instagram. So that's the fundamental problem, isn't it? How in the world do we take these gigantic, data-heavy images and shrink them down so they can just fly across the internet in seconds without, clogging up the pipes or filling up our phones instantly? Well, the answer is a really brilliant mathematical trick. Okay, so the first part of the answer starts with a technology you use literally every single day, probably without even thinking about it. I'm talking about the JPEG. And its secret weapon, it was actually developed all the way back in the 1970s. Pretty wild, right? So this image here, this is actually a famous one. It's been used for decades to test compression algorithms. Now, when you save a picture like this as a JPEG, the software isn't just randomly making it smaller. No, it's performing this incredibly clever kind of digital triage. So here's how it starts. The process breaks the image down into this grid of tiny 8 by 8 pixel blocks. So you have all these little 64 pixel squares, and each one gets analyzed and transformed all on its own. It's a classic divide and conquer strategy. And this is where the real magic happens. Each of those little blocks gets put through a mathematical process called the discrete cosine transform, or DCT for short. Now think of it like this. Instead of just listing all the pixel colors in the block, the DCT describes the patterns inside it. Is it a smooth gradient? Are there sharp edges? It's all about the frequencies of change. Okay, so the key idea here is that this transformation completely reorganizes the data. It groups the most important visual stuff, the things our eyes are actually good at seeing, into just a few numbers. And all the less important high-frequency details, they get pushed to the side. And this allows the algorithm to be absolutely ruthless. It can just throw away the data that we're least likely to notice, and that's what dramatically shrinks the file size. But wait a second, how can you just reorganize information like that? I mean, how do you cleanly separate the important bits from the junk without just making a complete mess of the image? Well, the answer lies in a really beautiful and powerful mathematical concept. So what is it about the math of the DCT that lets it deconstruct an image block so effectively? What's the secret sauce that makes sure all the different patterns it finds don't interfere with each other? How can we just discard some of them without totally corrupting the rest of the picture? The principle is called orthogonality, and here's a great way to think about it. Imagine you're tuning a stereo. You've got separate controls for the bass, the mid-range, and the treble, right? They're orthogonal, which just means you can crank up the bass without messing with the treble. They don't interfere. Well, the DCT does the exact same thing for an image. It breaks it down into these independent patterns, like smooth areas, sharp lines, fine textures, so it can get rid of one without messing up the others. So what this means is that orthogonality lets us do something pretty remarkable. It lets us take that complex 64-pixel block and find the closest possible approximation of it, but using only a handful of the most important patterns. That right there is the mathematical key. It's how you throw away data while still keeping the image looking good to our eyes. Okay, so now let's see how this same fundamental idea has evolved into something even more powerful. Because the very same principles behind JPEG compression, they're now being used to explore the absolute frontiers of science. This brings us to the core question behind a totally revolutionary idea called compressed sensing. It basically flips the whole script. Instead of collecting all the data and then throwing most of it away, compressed sensing asks, what if we could just measure only the most important information right from the start? And this diagram, it illustrates the process brilliantly. You've got the original image, and it goes through a transformation, in this case using something called wavelets, which are really just another cool mathematical tool for finding patterns. This isolates the essential information. Then a small compressed set of measurements is taken, and from just that tiny sample, an algorithm reconstructs the full image. I mean, just look at the result here. On the left, that's the original data. And on the right, that's the image recovered from just a tiny fraction of that data. It is incredibly faithful. The positions, the brightness of the star clusters, they're almost perfectly preserved. It's a perfect demonstration of the power of measuring smarter, not harder. But, for scientists, this isn't just about making smaller files. This method of intelligent compression can actually help them with their analysis. By transforming the data, you make the important features really stand out, which makes them way easier to find. Take a look at this, for example. On the left, you've got part of an astronomical image. Now, after the compression and reconstruction process, the celestial objects are so well defined that an algorithm can just automatically detect and isolate them, like you see there on the right. This is a huge help for astronomers trying to catalog stars and galaxies in these vast seas of data. So, I know it might seem like we've traveled from your phone all the way out to a distant galaxy, but these two ideas are so deeply connected. The math that was pioneered for JPEGs literally laid the foundation for the techniques now being used in astronomy, and both of them are absolutely fundamental to our daily digital lives. This principle of transform coding, using math tools like DCT and wavelets to reorganize data, it is literally everywhere. It's what makes streaming video on Netflix and YouTube possible. It's behind your FaceTime calls. It's inside your HD TV, your digital cameras, your MP3s, even medical imaging like ECGs. It is truly the invisible engine of our entire modern media world. And that brings us to what I think is the most exciting idea of all. This whole journey started with a really simple problem. How do we shrink a photo? But it's led to this profound shift in how we gather information. We have learned to capture more by measuring less. And that is opening up entire worlds that were previously impossible for us to see, from the most distant galaxies to the inner workings of the human brain. Which leaves us with a final, really fascinating question. What new realities will this math allow us to uncover next?